and good afternoon to you all. I've chosen this topic basically, and Jeremy has set a stage perfectly for me here by taking this on. But I'll be touching upon some of the photovoltaic technologies which has bearing on, on BIPV, which is Building Integrated Photovoltaics. So basically, I have arranged my talk based on these 5 points to touch the introduction part of it. I'll just talk about PV technologies in general and new developments which have been going on, some future trends about it, and summary and conclusion. Just have a look at the global PV scenario. Jeremy has already explained some parts of it. The global cumulative production surpassed 70 gigawatt in 2011. That was European PV meeting, where also it was announced that grid parity has been attained in some of the sectors already, and it will be achieved in major sectors by 2020. So all very positive news, and obviously you can see in 2010, it was amongst all the renewables, solar was one of the favorites among the investors. Coming to now building integrated photovoltaics, if you look at the built environment, obviously we have to integrate this technology into the built environment, and this is what makes a BIPV. How well can we connect them and how efficiently we can integrate them is a question. Now, if you look at the definition, very definition of the built environment, it also comes from, obviously, government definition on zero carbon homes. It says the built environment, although representing almost half of the all EU carbon emissions, presents the ideal least impact environment to both generate renewable energy and save energy. So, and if in that perspective, if you look into how the glazing market, which is again, is one of the established markets already with 6.6 billion meters square per year globally used. And this is worth about $51 billion worth of industry, euro based, that's the figure. Out of which the float glass was used up to 5.4 billion meters square, and while 80 million meters square was used for PV alone. Now, if you look at how BIPV is doing as compared to the established glazing market, you will find that it was 1201, which is 1 gigawatt peak in 2011, and expected to grow annually over the next couple of years at the rate of 56% to 11 gigawatt per peak by 2015. This is BCC research report. So combining with facade glazing and all BIPV applications together, this is around going to be about $100 billion of a pound worth of an industry, which compares very well with the current terrestrial solar PV market. So if you look at the promises that BIPV generates, it's really very, very significant, and it's going to be probably ultimate solution. When you're talking about BIPV market, I just cannot leave this part because I think glass market is very, very significant and main contributor to this BIPV application-based industries. And amongst all the frontline technologies which have been compared here, and if you look at how the development was going on and obviously how the glass market was moving, you will see there was a glitch around somewhere in 2011. There was a slump because of I think the growth was majorly affected from China and because of artificial crisis that was being created. And so it has impacted PV, module production in a way, and it has impacted also glass industries in a way. But it's catching up now, and it's estimated that the solar cell glass market will enter into recovery phase this year, reaching 10% increase over 2012 last year, And this upward trend will continue until 2015 with about more than 10% growth, which is quite satisfactory growth in considering that. But why I'm talking about these is because if you look at some of the technologies apart from, say, crystalline silicon technology, which is using oil-slick glasses used there also, but there are more functional glasses, such like transparent conducting oxide layered glass, which is used for most of the thin film PV applications, say for instance CIGS, cat telluride, amorphous silicon. These are the technologies which they use transparent conducting oxide glass as the base. I would just like to talk also about what are the technologies which exist and what are the ones which are coming up. So first generation technology, obviously, which was available was, and still is a strong force in whole of the PV market, is crystalline silicon. And it is estimated this will continue to remain as a market leader for at least coming, 20, 30 years, because R&D is also going on along with, say, crystalline silicon, along with other technologies such as second generation ones, which is thin film, amorphous silicon, cat telluride, and CIGS. You can see here these amorphous silicon and these materials were actually 1/100th of a thickness of crystalline silicon, but they can absorb same amount of light coming from sun. But the efficiency figures which I had taken were about 15% at module level, which compares little less as what crystalline silicon already have achieved. But the cost here is an important factor because better utilization of material is one angle, but also the module cost, which was exhibited by First Solar, American company, which actually for the very first time, it showed the module price below $1 per watt peak, and that was in 2009. And after that, now we know that crystalline silicon is also is going much below now $1 per watt peak, thanks to Chinese production. But I think it's also an artificial price which is there hanging now, which is almost like 59 cents a watt peak. So, but it still compares, with those value even artificially produced. And we are hopeful that it will significantly have bearing on future prices of the modules and price of electricity coming from solar. Third generation ones are new developments on, say, dye-sensitized solar cell and organic photovoltaics. Some very good kind of developments going on in this direction in terms of efficiency which have been achieved here is now crossing at the cell level also, it's more than 10% already. And this is believed that it is with the amount of R&D efforts going on to make it, the only drawback here in these technologies is the longevity of the devices, which is again given due attention, and hopefully we're hoping if 10%, say with 10% efficiencies and 10 years of lifespan, if these technology can really go, they can really have a very good impact on the solar PV market. Just to quickly tell you, this is how crystalline silicon module will look like. This is a monocrystalline silicon module, which you can see here. They're basically wired, and these are segments which are made from, say, wafers. And also this is a polycrystalline, which looks, the appearance of these will look something like this. And these are, again, a kind of p-n junction-based solar cells. With all the layers you can see here, N-type, P-type, and then we've got aluminum rear contact. Front contact is again, which could be silver or any other metal. But only thing which you can see here, what separates it from thin film PV is this whole thing is an opaque system. And in order to have light going through to the p-n junction, you have to have some areas which are not covered by metal. Okay, so that's where you have some shading losses coming or coming from these metal contacts which are which are almost like a finger sort of structure you will see on the surface, which is not the case in case of thin film PV, where you have TCOs, which are, and for that instance, I'm coming to amorphous silicon, which suggests that you have a glass coated with, say, transparent conducting oxide. This could be AZO, which is aluminum doped zinc oxide, or FTO, fluorine doped tin oxide. There are lots of TCOs available. And this is the structure which is for amorphous silicon-based cells. You can see this is P layer, which is about 25 nanometer, very thin. Amorphous silicon, which is intrinsic layer, is about 500 nanometer, and the whole stack is about less than a micron, which cannot actually absorb all the photons. Then has to be some kind of texture TCOs have to be made so that they can bounce back, and you can have a good light entrapment of those. The technology has matured very well since early 80s, and there's a company, obviously it has well, recession has impacted a lot of companies, and United Solar is one of them, one of the victims, which where obviously they were having triple junction cells on steel made and deployed quite significantly, have suffered. But yes, I would say this gives a hope, if they can be deployed nicely, integrated in a nice manner, can give solutions. And there are some examples of how they can be, integrated into, say, flexible substrates, which is difficult in case of crystalline silicon technologies. Another technology that I'm going to talk about is CIGS solar cells, which I tend to work on this technology as well. This is basically the structure of a technology where you have metal contact on the substrate, and then you have CIGS absorber. CDS is N-type material, so this makes a heterojunction, PN junction. And then you have TC on the top, which allows light to get in. This is a sort of internal structure, it will look like, and a cross-section of all these materials. I'm not going to go into details of that. But obviously, just to let you know the state of art of these technologies, how they're moving, you can see that 20.3% cells were made on glass, rigid glass substrates, which have now been surpassed, strangely, by a group in EMPA in Zurich. This is now a new established world record, and with 20.4% cells made on polyimide foils. And this is something very amazing, because the way things have moved, because it is believed that these foils, which are kind of polymer foils, will not have better efficiency. That was a kind of myth we had, but it's turning out very different in this kind of material. So you need right kind of expertise and knowledge in order to prove the point. And this is where I see has to be match of R&D and the industry is coming. So this is a recent development. I think in the last month it's happened. Another technology which you all know that has created a kind of, with the first solar getting up to 1 gigawatt capacity demonstrated in 2009. And so it brought the beginning of actually commercialization of thin film PV apart from amorphous silicon. And again, this is moving again. You can see 18.2% cells have been made by GE Solar, which is again a good kind of development. On EMPA, again coming here, chipping with almost 14% of the cells made. So these are some highlights, state of art efficiencies that's going on. And you can see this structure is pretty much similar to what we have seen in CIGS. Another technology that I want to talk about is dense dye-sensitized solar cells, which obviously this technology has a bearing coming from photosynthesis. Very similar kind of idea where you have titania spheres, TiO2, and they are actually covered, sensitized by the ruthenium pigments. And these make kind of nanocomposite solar cells. And unlike crystalline silicon solar cells, where same material can absorb and transport electron and holes, here it is happening slightly differently. You got two different set of materials doing the job together. So you have ruthenium dyes which are absorbing light, just like in photosynthesis. You have chlorophyll absorbing light and then allowing electron holes to move and do the reactions. Similar way, we got here ruthenium playing the role of chlorophyll, and electrons are injected into titania and allowed to transfer on the other end of the electrode, while holes are through iodine iodide electrolyte moving on the other side to give a photovoltaic effect. And this technology actually was invented by Michael Kretzel in, I think, early 1991. And already 13% kind of laboratory-based cells have been made out of this technology. This is one example of how the cells will look like, and these are bifacial cells. TCOs are used from both ends here, so you can see this is almost semi-transparent, depending on how thickness of these layers are like. And this is the one cell that I am demonstrating. This is obviously made by me at Imperial College in 2003, where we achieved 5.3% on plastic foils using all low temperature processing route. So the highest temperature we use in making these cells were 100 degrees centigrade and below. So these technologies, along with now organic PV, which is another topic of interest, obviously, amongst PV people. And this is, again, we got whole transporter organic material, organic semiconductor, and we got electron transporter. They can either be made in bilayer form, or they could just be made like a kind of bulk heterojunction form, where they can be made in finger contacts to cover larger area and better collection efficiency and separation efficiencies of electron holes. The state-of-art efficiency for this technology for single junction has gone close to 10%, which is a very good kind of improvement as compared to last few years when it was only 5 to 6% at laboratory levels. So considering all that technology, these were the technology I discussed are the frontline technologies, and how they look different. Obviously, this is crystalline silicon, you can see. If you want to integrate into the buildings, into facade or to windows, you will find that this will not be an ideal solution, actually. So that's where actually thin film PV comes in, which can provide kind of integration onto, say, glass or double glazing facades or windows, whereby you can maintain the transparency of the structure and having the aesthetic value of that. So this is one comparison of these two technologies. And moving on from there, actually, there have been some developments going on with my partners, collaborators at Glyndŵr University, Professor Stoterwine. And what we're trying to achieve here, and this was actually a TSB program with Arup, who were part of our team, and Pilkington Group. And here, the idea was to combine cadmium telluride solar cells, where we're thinning down this layer of cadmium telluride up to 300 to 400 nanometer in order to make them look semi-transparent. And then they can be integrated into the, say, double glazed units, whereby then you can, if you generate about, say, 8% cells, you're talking about 50 watt per meter square of energy generation at the same time, which is quite significant. And we have achieved, based on this, and the process that, the CVD process that Glyndŵr University they're using, we have achieved some of the results, the very recent ones, up to 5% for about 400 nanometer cadmium telluride layer, and CDS, which is about 60 nanometer, we could go up to 5%. And we know that there are certain limitations of fill factor, which is not inherent property of the device. So these are coming from the contact ends where there might be more shunt losses happening. So there is lots of scope where we can still improve upon this, which is the work is going on, and we're hoping we will have some better results to follow. Some of the new developments going on BIPV sector is the use of concentrated solar cells. So because we know we're limited, if you're trying to integrate, say, solar cells into the buildings, you'll be limited. You may be limited by the intensity, because the orientation of that cannot be kept always. It may not be always south-facing, or you might be having, you're integrating onto the windows, and you may not get the sunlight really directly coming on top of it. So there are concentrated solar cells being designed now, and this is one example of kind of compound parabolic concentrators, CPCs, which can be integrated into PMMA, which is a plastic material, or can be molded in a glass kind of with glass. And this can lead to a concentration from 4 to 10 times. So what essentially you're achieving here is that you're trying to have the diffuse light, which might be having 20% of the total capacity of insolation coming, that can be taken care of, and you can then enhance the capacity of it. So the conversion efficiencies will probably remain same, but the current will go up. So you will deliver more power coming from this. So this is one thing which is also going on. The cost of optics obviously is a critical factor here, which will compare how it will retrofit with the existing glazing and facade systems. But these are some new developments going on. Professor Tapas Malik, who was my colleague here, now is in Exeter. He works on this area, and we are working together on this as well. Future trends will definitely like to cover these application areas, and as Jeremy has pointed out, some of the applications could be where you can also have the aircrafts where the wings can be loaded with the PV kind of cells. This is a one tent which can be made flexible. This is a bus stop where this is organic PV actually utilized here. And some of the gadgets, electronic gadgets for small area applications can also be utilized. So actually, you can see all along with the BIPV, these are these applications which are also coming, and thin film PV will always have a lead here because thin film materials can be coated on any kind of structure. You can use flexible foils, you can use any sorts of substrate material there. This is a new thing which is developing, obviously, and obviously this was in 2008. You can see even crystalline silicon technology is also trying to move in the same direction, where if you can thin it down and can make them a kind of retrofit on in terms that you can make them bend, so they can be integrated well also into the building structure, or so this integration looks quite possible and viable. So these are some new developments going on, and with this I'd like to just summarize that, well, this is something, BIPV sector is backed by the established glazing industry, set to grow with this rate, which is quite substantial. And disadvantage of crystalline silicon is where, can be overcome by thin film PV, which is an opportunity, I would say, for thin film PV technologies, because at the moment, it's not able to really compete very well with the crystalline silicon prices, which have been really being dumped at the moment by China. And so I think this is one area where thin film PV has to be more active, and in fact we are pushing ourselves, the experts in this direction, into BIPV sector. So also thin film PV modules will allow greater freedom to select size and color, and then crystalline silicon module, such as module efficiency, it decreases with temperature. This is another element which I could not touch before, obviously, but temperature is one of the elements which has to be looked into carefully. Crystalline silicon will always have deficiency here in terms, because if temperature goes up, the performance of crystalline silicon module go down, while in case of it has less effects as compared to that on amorphous silicon or thin film PV technologies. Now the challenge lies in achieving the color neutral glazing. If you want to really retrofit into, say, buildings, the color neutral is the choice for most of the architectural kind of aesthetics values of those. And this is really difficult to achieve, because if you have a neutral color, that means you're talking about an absorber which is not in the visible range. And so you cannot utilize semiconductors for this property. But what actually then can happen is that if there's a freedom is to have for tinted glass appearance, then there definitely is a possibility. So it depends on where we are targeting our market, whether it's going to be the European side or going to be in Asia, where there is a bit of, likings can be different. And so the different color schemes can also work very well. Obviously, new concentrator PV designs are also coming up, and I hope that combining them with the thermal integration can make this industry a really very viable route. And with this, I'll end my talk. Thank you very much for listening.